Okay, so now we're going to move on to another type of test, and that is the chi-square goodness of fit test. Unlike the chi-square test of independence, the chi-square goodness of fit, in order for you to write down the null hypothesis and alternative hypothesis, they are not so cookie cutter. The way you write it, notation is still the same. The null hypothesis is H naught, the alternative hypothesis is H1 or HA, but there's no cookie cutter script like way for you to write this down. You have to read the problem and you kind of have to steal from the prompt. So there have been questions where it said that you were trying to determine whether or not the die you were rolling is fair. And so in that case, your null hypothesis could have been the die is fair, and the alternative hypothesis is that the die is not fair. Other times they tell you that you're trying to determine whether this model, let's say a normal distribution or a binomial distribution model, is a good fit for the data. In that case, you would say the null hypothesis is that the model does fit the data, and the alternative hypothesis would be exactly the opposite, which is that the model does not fit the data. And the main thing here is look at the words they are using. What is it that you're trying to determine? And then do your best to write down the null hypothesis. And the alternative hypothesis is always opposite of the null hypothesis. The observed frequencies, once again, should be given to you. In this case, to find expected frequencies, you're not going to put this into a matrix. The rest of these tests are put into stat edit. So you would have to go to stat edit. You're going to enter the observed values in list 1, and you're going to enter the expected values in list 2. These expected values, sometimes you have to, again, read the problem to see what the expected values would be. Let's say that the question says something to the effect that Jane is going to go to tutoring, and they write down the number of times she went to tutoring on a Monday, on a Tuesday, on a Wednesday, on a Thursday, on a Friday, on a Saturday, on a Sunday. And the expected values could just basically tell you that if you expect Jane to go to tutoring an equal amount of times each day of the week, and she has gone to tutoring for a total of 56 times, then how many times did she go to tutoring each day? Which is kind of like a lot, right? But in that case, 56 divided by 7 would be 8. And so your expected values would be 8 across the board. So it all depends on the problem. That's the thing about goodness of fit. It is not one size fits all. You really have to read the question. And that's sometimes what makes chi-square tests of independence easier. It is because it's almost done always kind of like the same way. So in this particular case, the degrees of freedom is just the number of columns or the number of rows, basically the number of, I should say, categories minus 1. And that's going to be your degrees of freedom. And again, the conclusion, nothing has changed. If your p-value is less than your significance level, then you reject the null hypothesis. If your p-value is greater than your significance level, that is when you fail to reject or accept the null hypothesis. Same thing goes with chi-square calculated versus chi-square critical, because this is called a chi-square goodness of fit test. They are both under the chi-square distribution umbrella. So if the chi-square calculated value is greater than the critical value, that is when you reject the null hypothesis. In the calculator, you're going to go to stat test, but this time the goodness of fit is option D. Okay, so let's go ahead and take a look at an example. In this example, it is from the May 2021 Paper 1 Time Zone 2 exam. A newspaper vendor in Singapore is trying to predict how many copies of the Straits Times they will sell. The vendor forms a model to predict the number of copies sold each weekday. According to this model, they expect the same number of copies will be sold each day. To test the model, they record the number of copies sold each weekday during a particular week. This data is shown in the table. A goodness of fit test at the 5% significance level is used on this data to determine whether the vendor's model is suitable. The critical value for the test is 9.49, and the hypotheses are, well, what's really nice here is that they're giving you the hypotheses, but still, pay attention to how they word the hypotheses so that if they had asked you to write them yourself, you would get an idea of how to do that. So in this case, the null hypothesis is the data satisfies the model, and the alternative, the data does not satisfy the model, because this is one of these model types questions. Then it says find an estimate for how many copies the vendor expects to sell each day. Remember I told you, this is one of those cases where they expect the same number of copies will be sold each day. They have told you the exact amount that they sold on Monday, on Tuesday, on Wednesday, Thursday, and Friday. Those are the observed frequencies. That it's actually finding out how many are sold each and every single day. So now we want to compare that to the expected amount. But before I can figure out the expected amount, I'm going to have to figure out the total. And then I have to divide that by 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. So let's go ahead and add 74 plus 97 plus 91 plus 86 plus 112, which is going to equal 460. And then 460 divided by 5 is going to give us 92, which means that the number of copies the vendor expects to sell each day is 92. It says write down the degrees of freedom for this test. Well, there are 1, 2, 3, 4, 5 days. So it's the number of columns or rows or categories. In this case, the number of days minus 1. So 5 minus 1 is going to equal 4. So the degrees of freedom is equal to 4. Write down the conclusion to the test. Give a reason for your answer. Okay, so we are going straight to this test. In the calculator, you're going to go to Stat, Edit, and you're going to enter the observed data in list 1. That is 74, 97, 91, 86, and 112. So that's the information that was given to you in the problem. Those are your observed frequencies, the exact amount that was sold on each and every single day. Then the expected amount, if you remember, is what we got when we divided the total, which was 460 divided by 5, and it's 92. So I'm going to write down 92 going straight down because that's the expected amount. Is your expected values always going to be the same for chi-square goodness of fit? Not necessarily, okay? So you have to be careful with that, but in this case, they are. So now I go to Stat, Test. You're going to go up to chi-square goodness of fit test. The observed values are in list 1, expected are in list 2. The degrees of freedom for this problem we said was 5 days minus 1, so 4. So now go ahead and press calculate. And so this is going to be my answer. The chi-square calculated value is 8.54. The p-value is 0.07358. And of course, the degrees of freedom, which we found, is equal to 4. When I go back to the problem, they have given me the critical value for the test, which means that I can make my conclusion by comparing the calculated value that we just got from the calculator and the critical value. If I do that, I'm going to say that since the chi-square calculated value that we just got from the calculator, which is 8.54, is less than the chi-square critical value of 9.49, because that's what they have told us, then we accept or fail to reject the null hypothesis and conclude that the data satisfies the model. And basically in a picture, in case you have forgotten, this is kind of like what the chi-square distribution looks like. The critical value in this case is 9.49. My calculated value is 8.54. Calculated versus critical works like a number line, a regular number line. So notice the 8.54 falls in the acceptance region. Therefore, that is why I accept the null hypothesis. Or I'm going to write down fail to reject. Of course, there is another way that I could have written this down. And that is that since the p-value, which we got from the calculator, of 0.07358, so 0.734, is greater than the significance level of 5%, which is 0.05, then we fail to reject the null hypothesis and everything stays the same. Like the rest of it just reads exactly the same. That's what we have written before. All right, and that's basically going to be the answer to this problem. And then this is what the mark scheme looks like, so you have an idea of how they're giving you points for this problem. Okay, so now we are going to do question number 4, which is from May 2021 paper 2, time zone 1. This is a question, it was a paper 2 question. At the beginning, it is a normal distribution problem. So we're going to get a chance to go over normal distribution. And then it goes into a chi-square goodness of fit test type question. So first, let's go ahead and work with the beginning, which is going to involve us reviewing how to put this into our calculator for normal distribution problems. It says the stopping distances for bicycles traveling at 20 kilometers per hour are assumed to follow a normal distribution. One of the good things about normal distribution problems is that they will always tell you it is a normal distribution problem. And so you know that that's what you have to do. The other distribution that you need to know for the applications and interpretation course is binomial distribution, and they don't necessarily explicitly tell you that it is a binomial distribution problem. Sometimes you have to infer that from the problem yourself. But here at least we do know that this is a normal distribution problem where the mean is 6.76 and the standard deviation is 0.12. Okay, so under this assumption, find correct to 4 decimal places. Pay attention when they ask you to round in a very specific way, because if you don't round to what they're asking you to, you're not going to get the last point. So the probability that a bicycle chosen at random traveling at 20 kilometers per hour manages to stop in less than 6.5 meters. So you're trying to figure out, this is a normal curve. The mean is right here in the center. It's 6.76. You're trying to determine the probability of x being less than 6.5. So 6.5 is right here. I would shade everything that is to the left of it. This shading of the normal distribution curve is considered my work. So now I can go ahead and put this into the calculator. To put this into the calculator, you're going to go to second, vars. You're going to go ahead and go to option 2, which is normal CDF, and then you're going to enter your lower bound as -1 E99. That is going to be set that way by default when you clear the calculator. That is negative infinity because I want everything that is less than 6.5. Your upper bound is going to be 6.5. The mean is going to be 6.76, and the standard deviation is going to be 0.12. So that is what goes exactly into your calculator. So we're going to go second, vars, option 2, normal CDF, press enter. The lower bound is negative infinity. It is there for you by default. The upper bound in this case is 6.5. We know that the mean is 6.76 and the standard deviation is going to be 0.12. If your calculator doesn't give you these options, like if it doesn't prompt you, that means that you're going to have to memorize the order so that you can write it yourself separated by a comma. And the comma is above the number 7. So that when I press paste, that would have been what you would have entered manually on your own. -1 E99, comma, 6.5, comma, 6.76, comma, 0.12. Okay, so it kind of, stinks if you don't have a calculator that prompts you to enter those values, but there is still a way for you to get the answer. In this case, the answer is 0.01513. And then remember, you want to round to 4 decimal places. So you would write down 0.0151. Okay, so now we're going to go on to part 2. I'm going to erase what you see here just because I want the space to show you how to do part 2. Okay, so now in part 2, it says, find the probability that a bicycle chosen at random stops in more than 7 meters. So if I want to show a drawing, I can, where the mean is 6.76. And now I want to determine the probability that it will stop in more than 7 meters. So more than 7 meters would mean that I would shade to the right more than 7 meters. Okay, so that is my work. So I want the probability that x is greater than 7 in this case. So now my lower bound is going to be 7. My upper bound is going to be positive infinity. My mean is still 6.76. My standard deviation is still 0.12. So this one's going to be a little bit faster because we're going to already have the values in the calculator. So in the calculator, I go second vars, option 2, normal CDF, press enter. In this case, we said the lower bound was 7. The upper bound is 1, E, which is second comma, 99. The mean and standard deviation haven't changed, so they stay the same. Press enter, enter again. So the answer is 0.02275. Because of that 5, and I'm trying to round this to 4 decimal places, the answer is 0.0228. And so basically that's how we're going to get the answer to part 2. All right, so then to continue the problem, it says 1,000 randomly selected bicycles are tested and their stopping distances when traveling at 20 kilometers per hour are measured. Find correct to 4 significant figures the expected number of bicycles tested that stop between 6.5 and 6.75. There is a difference between 4 decimal places and 4 significant figures. For example, if you look at the top answer, this one right now has 3 significant figures, and this one has 3 significant figures, even though they are both 4 decimal places. So you have to be very careful with your rounding. Okay, so we're going to go back to the calculator and we're going to find the probability, but because it says expected number of bicycles, we're going to have to find expected value by multiplying n, which is 1,000, times the probability. This formula is in your formula packet to figure out expected values. So let's go back to the calculator. Second vars, option 2, normal CDF. In this case, our lower bound is 6.5, our upper bound is 6.75. The mean and the standard deviation haven't changed, so I know that it's 0.45166. Now remember that this has to get multiplied by 1,000 because we want to figure out of 1,000 bicycles, how many would we expect to stop between those times. And so the answer is 451.7 if I round to 4 significant figures. So 451.7 is my answer. Even if you're thinking, how can you have a part of a bicycle? It doesn't matter. They want 4 significant figures. You're going to write down 4 significant figures. So the answer here is 451.7. Then I do the same thing for part 2, which is from 6.75 to 7. So back to the calculator we go. Second vars, option 2, normal CDF. In this case, we're going to change this lower bound to 6.75 and the upper bound to 7. Press enter and enter. And so that answer, it's going to get multiplied by 1,000 because we have to figure out the expected amount and we have to round this to 4 significant figures. So the answer is going to be 510.5. You're going to have to round the 4 up because the number next to it is 5. So this is 510.5. The measured stopping distances of the 1,000 bicycles are given in the table. It is decided to perform a chi-square goodness of fit test at a 5% level of significance to decide whether the stopping distances of bicycles traveling at 20 kilometers per hour can be modeled by a normal distribution with mean 6.76 and standard deviation 0.12. State the null and alternative hypotheses. Okay, so I'm going to go ahead and write them down here. The null hypothesis in this case is going to be that stopping distances can be modeled by a normal distribution with mean 6.76 meters and standard deviation of 0.12 meters. And I know you're probably thinking, do I really have to write all of that? And the answer is yes. If you were to look at the mark scheme, they would tell you that you needed to make reference to the mean and standard deviation. So then the alternative hypothesis would say that stopping distances cannot be modeled by a normal distribution with mean 6.76 meters and standard deviation of 0.12. And then notice I went ahead and I used the symbols instead of writing it all out again, which is acceptable, by the way. Okay, then for part D, it says to find the p-value for the test. So we are ready to put this into our calculator. We need to figure out, these are the observed frequencies. We have to figure out what are the expected frequencies. So the expected frequencies, number of bicycles, this data is going to come from the problem. Unlike the previous one that we did, where all of the answers were exactly the same, we have to stop and think about what we just found previously. It says the expected number of bicycles between 6.5 and 6.75 was 451.7, 510.5, and then less than 6.5. Remember that we previously found the probability, but we never actually multiplied that by 1,000. So if you multiply it by 1,000, you're going to get 15.1. And if you multiply this by 1,000, you're going to get 22.8. And so that is what's going to go into our calculator for expected. So now we have list 1, which is the observed, and list 2, which is the expected. And we're going to go to the calculator to run the test. Okay, so in the calculator, we're going to go to Stat, Edit. I'm going to clear what I had previously done here from a previous problem. So you go up to list 2 and list 1, you press clear, enter. And then we're going to go ahead and put in our new values. List 1 is going to be the observed frequency, so 12, 428, 527, 33. Then go over to write down 15.1, 451.7, 510.5, and 22.8. And like I always tell you, take those extra 5 seconds to confirm that what you have put into your calculator matches what you have written on paper so that you don't make a mistake. Because now we're going to go Stat, Test, up to option D, which is the chi-square goodness of fit. Where's the observed values? List 1. Where's expected? List 2. Degrees of freedom. We didn't talk about that. In this case, there's 4 different rows. So 4 minus 1 is 3. That's our degrees of freedom. Press calculate. So our chi-square value is 6.98 if you round to 3 significant figures. Our p-value is 0.0726542. And of course, degrees of freedom is equal to 3. One of the interesting things about this problem is that nowhere in this problem have they mentioned the chi-square critical value, which means that we actually have no choice than to just go ahead and make a conclusion with the p-value that we got from the calculator. So the p-value that we ended up getting from the calculator is the decimal 0.0726542. That is going to get compared to the significance level. So I'm going to write, since the p-value of 0.0727, because remember we're rounding to 3 significant figures, is going to be greater than our significance level of 5%, which is 0.05, then we fail to reject the null hypothesis and conclude that since we failed to reject, I'm going to restate what we have said, which is that stopping distances can be modeled with a normal distribution of 0.12 as standard deviation and the mean of 6.76. But you can go ahead and write that out by hand.